I think today we have a separate group. Good afternoon to all of you, and good afternoon from Sir Elkshid Ahmed. Its name is a little bit different. I think I'm pronounced.
No, he's Professor Ahmad Al-Sheikh. He's Professor Ahmad Al-Sheikh.
Al-Sheikh.
Al-Sheikh. Al-Sheikh. Al-Sheikh.
Yeah.
Okay.
Al-Sheikh.
So he's Professor Ahmad Al-Sheikh. Okay.
Al-Sheikh.
Al-Sheikh, yes.
Thank you. Yeah, I'm Kamala Gurunadan, as you all know, a highway consultant and fellow representative of the Council of the IESL this year, and chairperson of Knowledge Sharing Subcommittee of Civil Engineering Sectional Committee. Let me welcome you all to this webinar today under the subject from improving the built environment to improve the quality of healthcare, the evolving role of structural engineers, a well timely benefited title. I take the pride of welcoming you, Professor Ahmad Al-Sheikh, for today's webinar as the resource person from the offshore, but to be with us this afternoon and evening. I invite Professor Tishan Jayasinghe, Senior Professor of the Civil Engineering, University of Moratuр, as well as the Chairman of the Civil Engineering Sectional Committee, to give the introduction of the speaker today. Over to you, Professor Tishan Jayasinghe.
Thank you, Engineer Kamala. It's a great pleasure. First, a very good afternoon to all of you. It's a great pleasure to introduce Professor Ahmad Al-Sheikh, who was the former Dean of the Faculty of Engineering at Leopold University. And I first met Professor Ahmad a long time ago, about 35 years ago, and that was in Cambridge in 1988, October. And we both started our PhDs at the same time. And Professor Ahmed, maybe 1 or 2 years older than me, he came from the well-known University of Alexandria, Egypt, and he was a very, very bright student. I think he got the gold medal, and he's one of the best students they had. And he got admission to Cambridge University, and he did a very good research project on composite systems. And those days, I was very weak. Tried him programs on finite element method, and I always used to ask him. But finally, I never wrote any program on finite element, but instead I wrote programs on continuous bridge design using Fortran, and then I linked it with CE for Prolog and all that, and finished something called expert systems that we generally use in artificial intelligence. Whereas Professor Ahmed did very well, and he completed his PhD by August 1991. Then he joined Dundee University, and then after some years at Dundee, he joined the Leopold University. Later, he became the Dean, Faculty of Engineering. And about 10 years ago, he developed this interest in biomedical engineering, especially dealing with the human eye. And he used a lot of structural engineering applications on various deformations and so on to work out the best possible systems for the human eye. And I have been to his laboratory, very sophisticated. He has got huge grants, and he's one of the leading professors in this area of research. And he's a very bright person, and he's going to share his experience with you. So over to you, Professor Ahmed. And Ms. Engineer Kamala, how about our audience today? How many are having? At the moment we have 42, but I think we will improve. I will give a round of calls because there are some students who will be joining at any moment. So we'll start now, and Professor Ahmed will deliver the lecture now. Professor Ahmed, over to you.
Thank you, Tishan. Thank you, Kamala, and thank you for inviting me.
Yeah.
To talk to you. I think it would have been really, really good, to visit your beautiful country. I've never been to Sri Lanka, And
yeah, you are
I
most
would love
welcome.
one
And
day.
yeah, please come to
Thank
Sri
you.
Lanka one day with your lovely wife. And, if you want, you can bring your son and daughter as well. So we can have a wonderful time, 2 weeks vacation, visiting all the good places in Sri Lanka.
Thank you, Tisha. Thank you. I really appreciate that. So good afternoon, everyone. It's,
You don't feel to come.
I'm sorry. Hello. Shall I carry on?
Yeah,
Yes, please. Yes, please.
Please.
Yes, please.
Okay.
Yes.
Okay. So this talk is really about a change in my life that occurred to me as Professor Tishan has described. The talk is about our important role as structural engineers, not in the built environment, because this is what you would be most familiar with, but actually in improving the quality of healthcare. My background is very similar to yours. I was trained as a civil engineer, structural civil engineer, and I worked in buildings and bridges for many years until I attended a talk, probably like this one, where people were talking about the biomechanics of the eye, and really changed my life. I was really stunned by the potential of the huge contribution that we can make. And within 3 years, I decided to stop all activities and concentrate on this. And I never looked back, and it made a huge, big difference to me. And while in Dundee, I was an academic in civil engineering with interest in biomechanics. When I moved to Liverpool, I became a professor of biomedical engineering, although I still teach civil engineering, but my research is all in biomedical engineering. So my target my target today is really to explain to you what we can do as people with structural mechanics background in this field, and I'm hoping that I will be able to convince one or two or more to go and explore this field, and perhaps also have some contribution in that field. In our life, we're used to this. We're used to designing buildings, designing bridges. But when you talk to structural engineers, they don't talk about biomedical engineering. And I just want to touch on the things that we have done as a group, and our contribution to the fields. So starting with assistive technologies, it's a very simple field. It's basically to maintain people's mobility, and also to allow people who can't move to have a decent form of life. And it's starting with very simple elbow crutches and walking sticks to techniques that would allow people to get in and out of chairs and beds. And then to have things like wheelchairs and beds that can help you get out and in of beds. Medical testing has been developed by engineers. This is not people with structural mechanics background, but it's electrical background, and it's included in a way in my talk, although the focus will be in structural mechanics. But I think you will be familiar with lots of these techniques. Techniques to measure your blood pressure, to measure your pulse rate, to assess your heart function, using ultrasound and also MRI and CT scans to get some really useful insight into the internal organs of the body to help clinicians with diagnosis, follow-up progression, and also treatment. You will be familiar with some of these applications. So in the top left here, I'm talking about stents. For those of us who have problems with the cardiovascular system, and some veins or arteries, main ones can become partially or totally blocked. A really nice way of clearing the blockage is to have a stent that's basically a deployable structure squeezed together into a small package, and then you go through the bloodstream from a simple opening in the thigh, and then you navigate your way through the veins and through the arteries until you arrive at the place where you have the blockage, and then you release it. And when you release it, it opens up, it deploys, opens the vessel and allows the blood through. This technique has been with us for years, and it is our contribution. Intraocular lenses is for people who have cataract. The natural lens becomes cloudy, people cannot see. So what is the solution? The solution is to go in with a small incision through the cornea, go into the natural lens, break it down, suck it out, and then introduce an intraocular lens. Again, introduced as a deployable structure. It's folded into a small package, and then when it goes into the right position, you allow it to open up, and this becomes your new lens. This operation is very, 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 very common now. Hearing aids, and I'm also talking about pacemakers. So pacemakers are particularly important for people who have problems with the rhythm of their heart. The electricity system in the heart, if you like, is not working properly. And as a result of this, people can miss beats, and the beating can be irregular. So pacemakers is really a lifesaver in these situations. Prosthesis, for those people who had accidents or diseases that led to them losing limbs, losing parts of the body, prostheses have been incredibly useful to allow these people to go back to life, to be mobile again, to carry things, to go up and down the stairs, and even to play sports. These have been with us, and there has been huge improvement in the design and the implementation of this due to our contribution as structural engineers. Replacement joints is something else. So with age, with disease, and with accidents, people can lose the action of some really important joints in the human body. Engineers have developed, for instance, in the top there, hip replacement. So this is something that will be introduced, implanted into the femur bone, and then it gets locked into the hip. And with this, people can then go back to walking and even some gentle running after that operation. Before this, once you have this problem, once people have this problem, they are bedridden or have to use a wheelchair for the rest of their lives. This is not only in the hip joints, you also have artificial knee joints, and even artificial joints for your fingers. Essential, really essential technologies that are becoming more and more sophisticated due to our contribution. And then if you visit a hospital ward or a surgical, an operating theater, you will find that these have become really mechanical and electrical workshops. Lots of equipment there to sustain people's lives, to monitor their health, to offer them the drugs they need, to allow them to recover quickly and restore their health. This is all our contribution, and therefore, yes, the medical profession is very important, but really the medical profession cannot operate without our contribution. If you take out the contributions made by engineers to healthcare, you will go back to the dark ages. I'm moving now into my specific fields, and I will not be talking about. I think this talk is really intended for people who were not working in biomedical engineering before, and it's really kept at a general, simple level. But having said that, if you are interested, I will be happy to answer questions, or I will be happy to have email exchanges where I can provide people with more information if they are interested. But looking at ophthalmology or eye healthcare, the eye to me, is a mechanical object. And it's covered by the cornea at the front and the sclera covering the rest of the eye, including the back from the cornea backwards. The equilibrium of the eye is maintained under an internal pressure. This internal pressure is extremely important to allow the eye to maintain its shape. And because it maintains this ideal shape, light that comes from outside can then be refracted through the cornea, through the lens, until it meets on the retina, hopefully, so that people can see clearly. 70% of the refraction comes from the cornea, 30% of the refraction comes from the lens, and the lens is different from the cornea in that it can allow fine tuning. So you can change the shape of the lens, change its refractive power, so that you can see near objects and far objects. What is essential for clear vision, what is very important for us, is that these light rays that come from outside meet on the retina. If they don't meet on the retina, then you get a blurry image. So what's important? It's important that the cornea maintains its shape. It's important that the lens maintains its shape and also is clear. It's important that the axial length, or the length of the eye, this distance here, is adequate. It's important that the retina, which receives the light from outside, is healthy, and that the electrical signals that are generated by the retina go to the brain, reach the brain safely and in a satisfactory way through a healthy optic nerve. If you would lose any of these features, you would not get a clear image, and in some cases you would not get any image at all. Okay, so let's have a look at what can go wrong. So I said that the cornea must maintain a particular healthy shape. Sometimes you have a disease called the keratoconus, and this is localized weakness in corneal tissue that makes the tissue starts to bulge and thin. And as a result of this, the cornea changes shape and people start to see a blurry image, as you have on the left here. The word keratoconus is actually Latin for conic cornea. Kerato is cornea, conus is conic, so it means conic cornea, and conic cornea because it bulges. The cornea bulges outside, as you see in the bottom right image here. As I mentioned before, the lens, the natural lens can become cloudy, as you can see in the top image, and this happens lots of times, for many people, and it happens with old age, it happens with certain diseases, and it's before it was a big problem. People who have cataract, cloudy lens would just become blind, and that's it. It's lost. Their vision is lost. Nowadays, it's a very simple procedure, as I explained. You go in and you replace this lens with an artificial lens. Short-sightedness and long-sightedness, or myopia and hyperopia, is also now a big problem. And usually this happens when the eye globe, when the eye becomes too long or too short. This usually happens. So myopia is more common in young age. Hyperopia is more common in old age. There is a statistic that says that it's expected that by 2050, 49.6% of the world population will have myopia. That's a huge percentage. 50% of us, those of us who will live until 2050 will have myopia. 10% of these, 10% of the world population, 10 out of the 50% will have high myopia, which means that the refractive error of the eye is so high you know, we say it's more than 6 diopters, but just say that consider that it's so high that the eye has elongated so much, and this creates lots of problems, including retinal detachment, which I mention in a minute. But myopia is not about wearing glasses. You know, you would hope that it would stop at wearing glasses. Actually, it can have serious implications of the eye if it's allowed to progress. Retinal detachment is exactly what you see on the screen here, and it's most of the time retinal detachment is caused by the jelly material that fills the inside space here becomes insufficient to fill that space, and that's mainly because of the elongation of the eye. So this jelly material starts to pull the retina away from the sclera, and if this pulling becomes too big, too high, then it detaches the retina. And the problem is that the retina becomes separated from the nutrition it requires, and it dies. And as a result, people start to lose part of their vision, as you see in the image on the left there. You will notice that everything I say is mechanical. Everything I say is mechanical. This is another problem. This is, in some cases, the pressure inside the eye that I mentioned to you before. The pressure inside the eye, you can call it internal eye pressure, or you can call it intraocular pressure. Clinicians usually call it IOP, intraocular pressure. This pressure can become elevated, can become too high for a number of reasons. And one of the consequences of this is that it will press on the optic nerve head and damage it. And when this happens, people start to lose their peripheral vision. And this disease is called glaucoma. Now let's have a look at the solutions. The solutions that we as engineers have developed or have contributed to the development of. So the first one that I mentioned, I'll just take them in the same order. So people with keratoconus, they have an inadequate corneal shape, corneal bulges. So how do you correct this? People have invented corneal implants that can go inside the cornea and force the cornea to adopt a more satisfactory shape. That's a very, very mechanical solution. Another solution is to say, okay, this disease is caused by softening of, localized softening of the tissue. So what I can do is to use UVA cross-linking to stiffen the tissue artificially. And this technique is now used commonly, because this requires an actual surgery, while this requires sitting under a UVA linker, cross-linker, for 20 or 30 minutes, and it provides you with the increased stiffness needed to stop the progression of the disease. If you have a cloudy lens, as I said in cataract, this is the lens. This is one of the lens designs that people use, and as I said before, this operation is very common now. For those of us who have myopia or hyperopia, there are different forms of refractive surgery, and if you see the design of a refractive surgery procedure, it is mechanical. You know, it is absolutely mechanical. So in this particular case that you have on the I have drawings for, this is a myopia case. This is a short-sightedness case. How does the refractive surgery works? As I said, there are various techniques. I will talk about the most commonly used one, which is called LASIK. So in LASIK, what happens is that you use laser to separate part of the front tissue, the anterior tissue here, and this becomes something called the flap. Just take it, separate it from the rest of the cornea. Then you take the flap and bend it. Then you use laser to burn some tissue, lose some tissue, and then when this is done, then you bring the flap back. And because you have removed tissue with the profile that you need, you end up with a cornea that has a flatter curvature than before. Or if you wish, you can end up with a cornea with a more curved curvature at the center. So this can help you with myopia. It can help you with hyperopia, and it's now, there are now millions of surgeries like this done around the world, and as you can see, it is mainly mechanical. With retinal detachment, there are a number of techniques. The most commonly used technique, the easier one, is using laser, and basically laser would go and melt the retina tissue at the edge of the detachment. And why we do this? We use it to prevent the detachment from progressing. Another technique which is used mainly in Southeast Asia, I'm not sure about Sri Lanka, but I know that in China they use it, and it's called a sclera buckle. It's like a belt, introduced at the equator, at the middle of the eye. And the idea of this here is that it reduces the volume of the internal volume of the eye. Why is that important? Because, as I said before, retinal detachment happens because the jelly material inside this part of the eye has become insufficient. And this is why it pulls the retina away from the sclera. So by introducing this sclera buckle, you reduce the volume and you make the jelly material sufficient again for filling the space at the back, and therefore retina, either it doesn't detach anymore, it doesn't progress, or you may be able to force the retina to attach again. This is now the solution about glaucoma. So, as I said before, in glaucoma, the problem is increased internal eye pressure. Increased internal eye pressure damages the optic nerve head. Okay, shall I carry on?
Yes.
Okay, all right. So in glaucoma, as I said, the pressure inside the eye becomes too high. It presses on the optic nerve head and damages the optic nerve head. The main methods to control glaucoma and stop it from progressing is to reduce the internal pressure. So there are various ways of reducing the internal pressure, but you can't just simply reduce the internal pressure to any value or by any value. This requires accurate measurements of the internal pressure. So let's have a look at the way the internal pressure of the eye is measured. And you will see that it's very mechanical. So how does it work? You apply a mechanical force. Okay, right. So let me okay. So let me go back to this slide. Right. So I think I talked before about glaucoma and that it's caused by increased internal eye pressure. The only way to manage it is to reduce the internal pressure. But this requires an accurate method of measurement of that pressure. I need to know how much. I need to know how much the internal pressure is before I can reduce it. The method that people use to measure the pressure is very mechanical, as you will see. It's basically based on applying a mechanical force on the cornea, getting the corneal response, which is basically deformation, and then correlating this amount of deformation to the internal pressure. And the idea here is very simple, is that if the pressure inside the eye is high, the deformation will be low. And if the pressure inside the eye is low, the deformation will be high. So through a simple process of calibration, you can go from the corneal response to the internal pressure. The problem with this technique is that there is a clear effect of corneal stiffness on that method. So for instance, if you have a thick cornea or an old cornea, then this will give you the stiffness of the cornea will also resist the deformation. So this can give you a pressure overestimation, which is of course incorrect. So while the mechanical technique is simple, there are inaccuracies embedded in it because of the effect of corneal stiffness. So as people with background in structural mechanics, we are the ones who develop these techniques, and we are the ones who can also address this problem and offer clinicians an accurate method to measure IOP, to measure the pressure. I'm going to take you through. I think probably I should stop maybe in 5 minutes. So I'll just explain to you, how the road that I have taken to develop technology, medical technology that can address the questions that I posed. There is a set of steps that we use and most people follow if we are to develop a medical device or a medical process. You start with a concept design, and this usually comes from clinicians. They come to you and say that we need to develop something that can do this. You come up with a concept design. This concept design is then taken through a numerical assessment. And only when numerical assessment is saying that this design is likely to work, then you go and manufacture prototypes that can then be validated experimentally and clinically. All of these steps are important, but the most important step is the numerical simulation step. And in my group, we have put a lot of efforts in ensuring that numerical simulation is accurate, is representative, and we have reached a point where if the numerical simulation is telling us that this technology is likely to work, then we find that it usually works. But for numerical simulation to work, we need two things, two very important things. One is the topography, and the other one is the material properties. And while the topography is challenging, material properties is the main problem. And here you have two sub problems. One is that you need to develop accurate testing programs to get the material properties. And then the other challenge is how to take the material properties and embed them in the numerical simulation. So these two are two big challenges. Over the years, we have addressed these two. So we can read topography maps that are measured, basically elevation maps and curvature maps, exactly like what you do for your, if you have a site and you want to get an elevation map of that. We use similar techniques to get the topography of the cornea. So as I said, topography is not really a problem. The main problem is the material characterization. So we're used in our built environment applications to materials like steel and concrete and so on. And the material the biological material we're dealing with here has really complex properties. It has nonlinear behavior. It has hysteresis, which means that the unloading behavior is different from the loading behavior. It is viscoelastic, which means that it's if you load it quickly, you get higher stiffness. If you load it slow, you get low stiffness. The material also changes with age, becomes stiffer. With wound healing, becomes stiffer. Ocular conditions, with keratoconus becomes softer, and so on. So I think there is a Kamal, I have a feeling that would probably, I think I'll let me run to the end and just to give you the I think we're running out of time as well. So let me go to the end and just talk about the conclusions. So these are the messages that I really wanted to give you, and I'm really sorry, guys, that we got hacked like this. Okay. So if you are interested in biomedical engineering, and if you have any questions, that just get in touch. Professor Thishan and Professor Kamala will have my contact details. Get in touch, and I will be more than happy to answer questions. But basically, heart tissue mechanics, like bones, this area is very, very crowded. There's been significant progress. It is, for someone who's coming new into the field, it would be really difficult to make a contribution. Soft tissue mechanics, relatively primitive, and there is a lot of work that is required. And soft tissue mechanics, it will include a lot of things. The eye is one, the skin, internal organs, lots of things. Hearing, lots. The body includes lots and lots of soft tissues. The work in this area is multidisciplinary in nature. You must be in contact with clinicians working in your area to be able to work in this. If you work on your own, based on your understanding of what the medical problem is, then it's likely that you will produce something that may not be very relevant. I want to go to the points before last. In some cases, you will find that there are solutions. There are solutions for the problem that you're thinking about, but you will find that these solutions are quite expensive, and because of this, they cannot be afforded by most of the world population. And I consider this to be a real shame, because you did your research, you try to develop something useful, but then when it goes in the market, when it's translated into a device, it's so expensive, people cannot afford to buy it. So if you are interested in work in this field, I would very, very much recommend that you look at solutions, that you look at problems that have already been solved, but the solution is too expensive, and you try to provide a solution that can be afforded. Okay, and then my final point is that this is very, very satisfying. Personally, you feel that you're helping people, you're making a difference to people, you're allowing people to see. You see, this is very, very important. And I think perhaps I will stop here if you have any questions. Kamala?
Yeah, Professor.
Right. So, are there questions, or shall what do you think? Just to the, I'm really sorry. I had to cut it short because of the hack. It's.
Your all slides done, Professor?
Yes, I think so. Yes. Are there any questions for me, or what do you think?
Chat box, of course. Yeah.
Kamala?
Yeah, Professor. I think we have come to the end of the session.
Okay. So I'll just it's I think it's a shame about what happened in the last 10 minutes, but I think these things are can happen and will happen, I'm sure, to lots of people in the future. I just hope that this talk was useful to you, and would persuade perhaps some people to
So,
Uh,
Professor
one
Ahmed, I mean,
explore.
I have been checking the chats and we don't have any serious questions on the chats. So what we do is, okay, it's a great insight into the kind of things that we can do as structural engineers in the related fields and also in biomedical engineering. And at our university also, we are having biomedical engineering, a small number, and we are actually promoting the MIDAS software for them to do the research on the MIDAS FEM. It's a version which will allow us to do research on materials that are strong in compression, weak in tension. So we are actually, they all have access to that kind of software. So basically, now it is coming to a level that because we are using the same kind of tools like finite elements and so on. And so it's a great, it's a great privilege to have you as one of the resource persons. And so I wish to thank you on behalf of Civil Engineering Sectional Committee for taking your time amid the busy schedule. And I'm sorry that there were few disturbances, unforeseen disturbances. But it was a great, it gave us a very clear message. And thank you very much, Professor Ahmed.
Thank you. Thank you, Professor.
Thank you.
Thank you.
Right.
Thank you.
Thank you.